Okay, so now let me explain what a functor is. So a functor is a class, right? Like a class like equals and semigroup and monoid and so on, right? It's a class. And I'm going to use prime because it's already defined in prelude, right? So we need to use a different name. So it's a left, right. Yeah, it's pretty hard to talk when like right is a word that I say so often. It's hard to talk about eithers. Right, so we have this class functor for some type f, right? And we say class functor where, and we have a function called map, but we'll use map prime here because again, map is already defined. Which is like this: for all a, b, if you give me a function from a to b, and then fa, I'll give you back an fb. And here's the tricky part. The tricky part is that this is what a higher kind of type means, right? So, and let me go back for a second. So either, and maybe, and list here. Let me grab all of them and like copy them and move them all in the same place, right? And let me, what did I do? Okay, and then let's search for where is either. Okay. Okay, so let me paste them all here, right? So these are all higher kind of types. Why do we call them higher kind of types? Well, because basically list, like if you just type list, it lists on its own makes no sense, right? It's like it's nothing. You need to say list of a or list of int or list of string. Even list of lists of string. That's totally fine, right? But like just list on its own, it does not make sense, right? And same with everything, right? Same with maybe a, only maybe a makes sense, right? So in a way, we can kind of say that, you know how we say that some, for example, function f is a function from int to int? Well, we can kind of say that list is a type function from type to type. Right? Because you need to give it a type, right? For example, int is a type, right? And string is a type, right? But list is a type to type, but then list int is a type again, right? Because you apply this to this and then you get this, right? Right, and again, maybe is type to type, right? And then either is even stronger, right? Is type to type to type, right? Because it has two type variables. Right? Because if you say either string, you still need one more thing. Right, so it needs to say something like either string int to get a simple type, right? Okay, so then when you write this line here, the compiler doesn't know what you want f to be, right? But when you type this line here, and if the compiler, so here, f is totally unknown. It can be anything, right? But here, when we write fa and fb, the compiler now knows that f must be like this. Does it make sense? Because we write fa, right, one next to each other, and this only makes sense if f is of this type. We also know that a is of type and b is of type. How do we know that? Well, let me explain. We also have this thing, function from, like, this function is type to type to type, right? Because if we write int to string, this is a type. It's string. Thank you. But we can also write, for example, okay, the syntax is a bit weird, but if you write it like this, then it's type to type. And it's kind of like int, like so, but we like it's kind of like this, but you cannot write it like this.
Okay.
Right? So because we know this about functions, we know that left-hand side and right-hand side need to be simple types, right?
Yeah.
So that means we know A and B need to be simple types, right? And that's why you know that F needs to be this sort of thing, like a like one level higher than simple types.
Okay.
Right? Okay. So this is like a super useful thing because it gives us it gives us a class of things, right? Which basically allow us to say, okay, given some f of A, we can go to f of B, given a simple A to B function.
Yeah.
And we've seen this for lists. Like we've implemented it for lists somewhere here with map list. Oh, where is it? Oh, actually we didn't do map list, but we'll do it now. We see it for maybe here, map maybe, right?
Yeah.
And we see it for riders here. We'll see which one is the correct one that we need to use. It's one of these, and we'll figure it out, right?
Yeah.
But it turns out it works for a lot of types, right? A lot of types have this map function. It's very, very useful. It's one of the most useful things. And you might have seen this function as in C# as select. You might have seen it in JavaScript or other languages like map, or I'm not even sure if it has what other names it might have. Map is the most useful, most common one. Okay, so let's try writing an instance for, well, let's write the easy instance. So let me write one for you. Maybe functor. And then let's say functor, maybe. Right, so here, because this f needs to be this sort of thing, here we just say maybe, right? This is one of the very few places where you can write maybe without a type next to it, right? You don't need to say maybe int or something, right? You have to write maybe because the f is like this, right?
Yeah.
And then we have map prime where you take an a to b function, right?
Yeah.
And then we take a maybe a, so it's like nothing or something, like some maybe a, and we need to return a maybe b. But we already implemented this. It's map maybe a to b ma. Okay. All right, it needs to be functor prime. You're correct. Thank you. Right, and we already implemented it.
Yeah.
Okay, so do you want to try writing the one for lists, and then we'll figure out the one for iders.
Okay. So it's instance the list functor.
Yep.
And it's a functor right, of list. Okay, where? Okay. So how do I map lists? So I have the first one is an A, and
no, it's still it's like okay. Let me try to explain for a second.
Still a function, right? Because
yep. So it's like here we also have for all A B and then A to B and then maybe A and then maybe B, right? You still write this here, and here you can also write this if it helps, right? You can copy it here, like you literally just copy paste it, and then the thing you do is okay. What do I replace? I replace list here and then list here, right? That's all that I replace.
Yeah.
Okay.
So it's again map prime. It's so first of all it's A to B. And now I have the pattern match.
Yep. Exactly.
Was it this?
And then you also have a rest, right? Don't forget, because cons always takes two things. Okay.
And it's equal to map. No. Okay.
So maybe let me write an example here for you, right? Maybe that will help you. So let's say you want to map show over 1, 2, 3, right?
Yeah.
So what's the result of this? Well, it's 1, 2, and 3, right?
Yeah.
So you're right in the sense that you need to call it recursively at some point, but you kind of need to keep the same structure.
Okay.
Right, which means that you kind of usually when you see that the structure is the same, usually start with the constructor.
Yeah. Okay.
Okay.
So it's A to B and of A and the rest.
Yes. Well, okay. So let's first of all, this needs to be parenthesized, right? Because it's
Yeah.
you need to call. Okay. So another problem is if we save this, I think we'll get a decent error. I hope. So it's saying okay, cannot match type A to B. What it really means is that rest, this thing is type list A.
Yeah.
But this so far is a list B.
Yeah.
Right?
Yeah.
So do I have a way to go from list A to list B?
Yeah, with the functor, right? I mean,
Exactly.
that's what
With a recursive call. Exactly.
it's doing. Yeah. So, where do I use it? I
Instead of
think
rest. Yeah, exactly there. Yep.
and I still need this actually. And yeah, but do I call? Because in my head I call this.
No, you just call map, like the map function.
Yeah, I call map again. Okay.
Mhm.
Prime of rest.
Okay, but then okay. So first of all, you need to parenthesize this.
Oh, sorry. Yeah. And
okay, and what else? What else is missing?
well, map needs two.
Mhm.
So it's. Is it A and rest? Like,
Well, no. What type does map need as the first
B and
argument?
rest, right?
You don't even have a B. It's a function. It's just
yeah, but
yep, that's it. You just need to pass the
I
function.
thought I can replace A to B with B that way.
No, because like you're going the rest, but to the same thing, right? Still with A and B, and then you have
Yeah.
one more error if you can.
Okay.
It's just saying that you don't have a case for nil, right?
Yeah.
It needs to go below the.
Oh yeah, I don't know why I put it there.
Okay.
Okay. So if I get whatever and nil,
Mm-hmm.
it goes to
It's as simple as you think it is.
okay.
Yep, exactly. There you go. And
Okay.
that's
So
correct.
my biggest problem with this was that on the functor that you did, you called it map prime and then you used map maybe.
Oh yeah, because we had my map maybe here. So, I see why. Okay, because we defined it here, right? As a where is it?
Yeah. I was looking for map list so I can see
it's here,
what.
right? But we didn't define that one. Okay, I get it.
Yeah.
Of course, we could have just written the same implementation there, and it would be the same.
Yeah.
Right, I just didn't. Yeah, I should have probably done that.
No. It's just me being silly.
Okay, so let me show you a different instance, either functor.
Yeah.
Okay, so another thing is if we write either here, do you see the problem? It's tricky. And again,
No.
this should be also functor prime. So f here needs to be type to type. But either is type to type to type. It's one more, right?
Yeah.
So the thing is, how do we get to one less? Well, we just say either of some A.
Okay.
Right? But then what does this mean for our thing? So let's copy this, right? So how do we replace this? Well, we replace f with whatever we have here.
Okay.
Right? Let's say either R instead. And you'll see why in a second. Right? So we replace f not with either, but with either R.
Okay.
Right?
Yeah.
So the idea is here is that okay, we can map we can map the either, but we have to map the right side with a functor.
Yeah.
We cannot map the left side with a functor. And the reason for this is that basically the position of arguments matter, right? So always when you see like let me write this down somewhere. So for any type, for any higher kind of type, like T, right? If it has more than one argument, for example, TABC, right? You can only use functor to change the last argument, right? So we can go from TABC to TABD using a C to D function, right?
Yeah.
So again, remember with map, we can only change the last one, right? No matter how many we have, right? If we have 10 more here, we can only change the 10th one, the last one.
Okay.
Okay, do you want to try implementing this?
I can try. Okay. So, first of all, we have an A to B. And now it's either of are A. So we have to construct to pattern match. But okay. So do I pattern match like this? Is this correct?
Well, okay, it's an either, not a, so the constructors are left and right, not cons.
Oh yeah.
And it's just left R or right A in your case, right?
Yeah.
So if you have a left R, what can you do?
If I have a left R, wait, give me a second. Left R.
You can just type R there, yep, and then do equals.
To
yeah, okay. Yep, correct. That's all you can do here. Again, my usual comment of you don't need the parentheses there, but that's fine. Okay, so what else? What else can you have? You can have a right A, right?
Yeah.
Okay.
And it equals to so here it tells me it should equal
yes, that's good.
Is it? No, this one's
it's
not.
good so far.
Really? And the B?
Well, you don't have a B, right? But A to B needs an A, and do you have an A?
Okay.
Yeah, you do.
Yeah.
Right? And then again, you okay. Let's try saving and see what kind of error we get. Yeah, this is a complicated error to figure out. So the problem is you need to like parenthesize this, and maybe you don't even need to parenthesize this, right? Because like you need to do like A to B first, or also you could do this, for example. So let me show you a different version. You could, oops, what did I do? You could do something like, okay, let B equals to A to B A, right?
Yeah.
In right B. Maybe that's easier for you to read.
Okay.
Right, because, okay, I get a B value by applying this to this. And then if I have a B, I just do right B. Get the either. Right? So if in doubt, just use this syntax. It helps a lot.
Yeah.
Okay. So we have all the functor instances. So that's what functor is. That's everything that there is to know about. Well, not everything. It's there's a few more things to know about functor, but an interesting thing about functors is that you cannot write a different implementation, right? The functor cannot do something else, which is pretty cool, right? You kind of know from the type signature that it will literally just can only do this. But I'll talk about that more at some other time. Okay, let's figure out the homework because it will probably take a bit.
Okay.
So let's see, more list functions. Cool. So let's see what other list functions we have here that we didn't implement. We did counting, right? Sum. We can do sum. let me write some functions for you that might be a bit complicated, but so what's this usually called? Let's call it like this. Say if we have a monoid M, I want you to, if you have a list of M's, I want you to give me an M back. And the idea is note that you have to use both this and to solve it.
Okay.
And I want this is hard, right? So this is let me say hard. Okay, just so you know, right? You can do them in a different order. Maybe we'll reorder them such that the harder ones are later. Okay, sum and products. Okay, find count. This is kind of counting how many things. Oh, that's boring. Prepend, append, map. Oh, we had map for list, but only for this version of list. Okay, so we have folds. Okay, let's do the simple folds, like the regular fold. Again, not very simple, but you can look at the one that we've defined here and maybe get some ideas. So hint. Okay, so we kind of need for all a b given a b and an a to b and a list of a. I want you to give me back a b. Okay. And then I write a bad implementation just so it compiles, right? But this is bad, right?
Yeah.
You're supposed to use other arguments unless otherwise specified. Okay, sum, product count, find count. Okay, what other things we did here for lists? Fold to string, show. What other cool list functions can we define? Guess we can cheat and look at like at pursuit and see what kind of things exists for lists. So let's look at pursuit. Let's the list module and like get some ideas for functions from here. Data list. Range. Nah, that's boring. Sum. Many. No, too hard. Length. We have length. Do we have length? We don't have length, right? We didn't implement that. Okay, oops. Let's do length, I guess. So let's say so for all a, if you give me a list of a's, I'll give you how many. And again, of course, returns how many elements are in total. Okay, oops. What other things do we have here? Length, insert. No, we don't want to do sorted. Head, last. Tail, index. Oh, this is an interesting one. Okay, this again might be a bit complicated, so if you get stuck, so given a, I want you to give me an index and a list of a, and I'll give you maybe a. And this is kind of combining both things.
Okay.
Nothing. So the idea is here, so for example, index 0 of 1, 2, 3 will give me just 1 because it's the first item, right? Index 1 of 1, 2, 3 will give me just 2, right? And the index 10 of 1, 2, 3 will give me nothing because there's nothing at that index, right?
Yep.
Okay. Okay. We can skip all of this. Filter, map, maybe. Yeah, we will do this together at some point. I don't want to do that take okay, I don't want to do too many list functions. That's enough. Let me think. So we have maybe and either. I don't also don't want to do too many of those. Okay, let's allow fold here. Okay, let's move this first because this is a lot easier. Is just, which is a function from for all a, maybe a to boolean, returns true if the constructor is just, right? Kind of like the is nothing version, right? And then is right. I don't think we implemented this, right? We implemented this left, I think. Yep.
Yeah.
For all a b, either a b boolean. Again, returns true if the constructor is sorry, it's what's it called? It's
just or
it's right. Sorry,
no, nothing. No.
It's right in this case. Okay.
Yeah.
Right. So what else can we do with this? Let's just have a look at these things. I want to do a few functions for maybe and either. Perhaps from maybe we'd have that. It's just optional. Okay, nothing too interesting here. What about either? I have one idea of like two functions. Let's see if there's any others. Choose it, no. Yeah, note and hash. Okay, let's do note and hash. That's what I was thinking. So note, if you give me an A and a maybe B, I'll give you an either A, B. So the idea is here, if I have note of error, well, we cannot divide, missing value, starting from nothing. I expect you to give me back left missing value. And if I give you a note of, thank you, missing value for just one, I want to give me back right one.
Okay.
Right, so it's kind of like, okay, I want to go from maybe to either, right?
Yeah.
So how do I do that? Well, I give you the value for A, right? For the like A, right? So if you have a value, you put it in the right. If you don't have a value, you take this one, right? And they'll do the bad implementation, it'll figure out the correct one. So I want hash left of missing value to be nothing, and I want hash of right one to be just one. And hash is the opposite, right? So hash goes from either A, B
So maybe
to maybe B, right? So hash is, I'll just say it's nothing, but of course there's a better implementation. Oh, and okay, let's not forget for alls.
Yeah.
Okay, what's the, okay, we need to ignore the argument here and here. Okay, so let's see what else can we do. So it's not hash length. Okay, that's enough for this. And then you have this, which okay, wrong implementation, you need to figure it out. Okay, and then let's see, I want to give you some types. Okay, so let's say define functor instances for the following types. Okay, so I want you to do it identity. So these are some types. Okay, that's enough with sum types. Okay, these are kind of simple. This is sum, sorry, product. Let's do a couple of sum types. Let's do sum one. Okay. That's enough sum types, and then maybe one more recursive. So this is either empty or let's say leaf. Okay, let me see. Let's just use the same type that we use for trees here, because I don't remember which type we used. What was the type that the tree type? Okay, so it's empty or okay. Okay, so empty or node which has 3a, a and 3a. So what did I get wrong here? Other pair. Did I use the same name? Type arg. Oh, okay, sorry. This is like so. My bad. And I actually wanted to do the other way around. So let's say BAB. Okay. My bad. Okay, I'm pretty sure that's quite enough.